And I wish at the Braves game they would have chosen me, because they were like, this was the question: how many people in the audience, or how many spectators has there been since the first game, like in total? And like, I was 10,000. No, I was about 22,000 off.
Huh.
Because I
for this season?
Yeah, like how many people have been in attendance? Like, so count out everybody that's ever gone to a game. They guessed like 200,000, 100,000. I was like, what? It's like 700,000, because I like just did the math really fast in my head. It was 677,000. Because you know what the winner got? Whoever they were with got to go move down to like better seats.
Oh.
And I was like, I was just like, it's like 700,000, and then it was 677. I was like, I was so upset.
You're fine. So sequences of functions is something that you...
Are we still on the end Pythagorean paper?
Yeah, we're in the end Pythagorean theorem paper, and so we've sort of picking up more or less where we left off in terms of, I want to just quickly share with you the results that we found concerning basically the theory of power series, how calculus works for power series. And so to prove those things, you need to understand a little bit about sequences of functions. And I figured this is good for you to hear anyway, because you haven't had the analysis course yet.
Yeah.
And there's a significant chance your real analysis course will not get to this anyway, because like, if I was teaching it, I probably wouldn't get to it either. But one of the principal problems of analysis is, like, when there's more than one limit at play, can you change the order of limits?
Mm-hmm.
And this problem fleshes itself out at the level of a different question, which is like, if you've got a sequence of functions, does the limit function have the same property as the functions comprising the sequence? So a standard example of this sort of thing, and this is just from like real analysis essentially, but if you have fn, as you know, from the closed interval 0 to 1, all right, to r, where fn of x equals x to the power n, right? I think that's it. Then maybe remembering this wrong. No, it's fine, it's fine. Then, you know, this gives us a sequence of functions, right? And you probably haven't thought about a sequence of functions before, but, you know, you can ask the question, what's the limit as x goes to x naught, let's say, of fn of x, right? And what is it? It's x naught to the n power, right?
Yes.
Okay, great. And so let's see here. Another question. Fn of x equals x to the n. What can you tell me about those? Well, I think we could both agree that these are continuous functions, right? Continuous on 0, 1, right? Okay. Now let's graph. Let's graph some of these. See, we can. So n equals to 1, 2, so forth and so on, right? Here n is a natural number. So x equals. So we're going from 0 to 1, right? So first one, n equals 1. That's y equals x, right?
Yep.
So there you go. There's n equals 1, right? What's n equals 2 look like? Well, parabola. Right? Cubic. Well, it's below the parabola, right? And what happens? N equals to 4. Well,
You get a bump.
more of the same, right? It just keeps blowing out, right?
Yeah.
Right. And so as n goes to infinity, what do you get?
You get a closer and closer, like, horizontal line.
Right, you get this point here, right? You get that horizontal line all the way over to 1, right?
Mhm.
But actually, at 1, it goes up to here, right?
Oh, it's just, yeah.
And so what I'm saying is this is y equals f of x, where f is the limit as n goes to infinity of fn. The red thing I've graphed, that's the function to which this sequence of functions limits.
Yes.
And notice that the red one is quite clearly not continuous.
Yeah, it's not.
Because it jumps.
See,
And so at the level, yeah.
but while I understand that is the answer, like that never would happen. The closer and closer you got to infinity, it would shoot like it, you know? Like how can you prove it's discontinuous? It becomes like a limit. The closer you get to it is to infinity, or the closer you go into infinity, the more it will approach discontinuity.
Well, I mean, I guess that's the difference between, halting the limit process and actually letting the limit process go away,
Mm-hmm.
There is a difference.
Like that's the obvious answer is that that's exactly what's going to happen, but how do we know?
So
even if you took the biggest number in human conception, it would still look like a smaller.
right, so this for every n,
Mm-hmm.
right, for any fixed n,
Yeah.
that's just x to the n. Limit of x to the n is x approaches 1 from the, I should say left, I'm an idiot. Don't tell my Cal 1 students, sorry. I mean, that's 1, right? What's the limit of 1 as n goes to infinity?
The limit of 1 as n goes to infinity?
I mean, limit of a constant.
Yeah.
It's-
Oh, yeah.
It's just 1,
Sorry. Yeah.
But on the flip side, this right here is what I'm calling f of x, the limit function. I've graphed it here, right? And the limit is, as this approaches 1 from the left,
It'd be 1, or it'd be
I guess
0,
it's still,
right?
actually, I actually think it's still 1.
Yeah.
Haha.
Well,
That's
wait.
funny.
As n
That's
approaches
funny.
f. No.
Actually, this is not a good example. This is still equal to 1 because this approaches 1, but it
Yeah.
doesn't actually equal 1. So, like, this is still 1. This is not a good example of what I'm trying to get at. I'm sorry, Audrey.
Oh, it's
Um,
okay.
But it is nevertheless the case, this much is true, which is that, well, anyway, it's still, my claim that the limit function f is not continuous is still true, because 1 is not equal to f of 0, right? F of 0 is, oh, excuse me, I'm an idiot. Don't let me talk you.
I thought, yeah, the limit is.
The limit is
x.
what? Yeah, tell me again, what's this limit?
Wait, which
Good
one?
grief, what's wrong with me?
As n goes to infinity?
Yeah, as x goes to 1,
Why?
as x goes to 1 from the left.
It gets closer and closer to 1, but then it jumps.
Right, but the limit doesn't concern actually at 1, right?
Yeah.
It's numbers approaching, but not equal to 1.
Yeah.
So this is, it's
0.
0. Right. Which of course is not equal to f of 1, right? Which is 1.
Yes.
So, I mean, this is probably the most famous example of interchange of limits.
Not being consistent yet.
Right. So, whenever in analysis we have two limiting processes and we interchange those,
You don't get the same thing.
may or may not get the same thing.
Is there a word for when you do get the same thing, like when limits are associated?
When the
Commutative?
commutative maybe, but I mean, there's a lot of different kinds of limits,
Yeah.
and there's a lot of different scenarios where it does hold, and so yeah. But this is why we have to be careful about sequential limits, among other things. Is like the order of limiting processes can be tricky. Now, one of the principal properties that helps you be able to exchange limits is what's called uniform convergence. So this is my definition 5.14. We say a sequence of functions on a subset of the algebra converges uniformly if, here I'll write it. Can I erase? Yeah. So uniform convergence definition, you have Fn from some subset of the algebra to the algebra again is uniformly convergent well, excuse me, that's not what I mean to say. I mean, this is, well, I guess it is what I meant to say, but I'm just fussing here. Uniformly converges to F. All right. If for each epsilon greater than 0, there exists m in the integers, natural numbers, such that n greater than or equal to big N, I use m, n greater than or equal to big M implies that the norm of Fn of z minus f of z, closed norm, is less than epsilon for all z. In E. So the sequence I just erased was not uniformly convergent because this, like we couldn't get that criteria to hold for z equals to 1. For z equals to 1, we had like the thing we would like for the limit function to be. We had f of 1 was 1, whereas these ones are 0 as n gets further and further out. They're arbitrarily close to 0, so we couldn't force those to be small as epsilon. There's John. So this is uniform. Uniform convergence looks like this. So the thing, like non-uniform convergence would be something like this M. Notice that the key feature here of the uniformity that we're talking about is that this M is independent of Z. Like it's independent. Independent of Z in some sense. I mean, I guess technically, well, anyway, let me shut up about that. Okay, so, let me erase that. So it is likely you'll talk about uniform, actually, I hope you talk about uniform convergence in real analysis. I mean, I think it's a natural topic there, but the series, if we have a sum, Fn of Z, this converges uniformly on E if, what does it mean for a series to uniformly converge? It means that the sequence of partial sums converges uniformly on E. So the sequence of partial sums looks like this: Sn of Z, it's the sum, let's say I equals 1 to n of Fi of Z, right? This is our usual thing to discuss convergence or criteria for series. We, talk about the corresponding property for the sequence of partial sums. Did you do this in Calc 2 or no?
So one more time, sorry.
The defining series is the limit of the sequence of partial sums. Does that ring a bell from Calc 2 or no?
So defining limit as a series of equal partial sums, that means, would that, no, maybe, but I'm thinking kind of.
So just forget about functions for a second, like a numerical series. The sum, let's say k equals 1 to infinity of base of k. What does it mean for that to converge? That means that the limit as, n goes to infinity of the sum k equals 1 to n of base of k exists, right?
Mm-hmm.
This,
that doesn't converge.
this is a sequence of partial sums.
Yeah. Oh, it could converge, I guess. Okay, I'm with you.
So the sequence of partial sums, it's like, you got A1, then you got A1 plus A2, A1 plus A2 plus A3, and so forth, right? So to define convergence of a series, we always define it in terms of the limit of the sequence of partial sums. That's all I'm saying. Still true when we look at a series of functions. A series of functions converges if the limit of the sequence of partial sums converges. Although now I'm saying converges uniformly, which is
No, but that makes sense.
So uniform convergence is a stronger kind of convergence than pointwise convergence. Pointwise convergence is like, well, let me not belabor these things. Let's see here. Now, so my theorem 5.15, theorem 5.15 in the N Pythagorean theorem paper with Daniel Fries, it says that the sequence of functions converges uniformly if and only if it is I would say pointwise Cauchy. So theorem 5.15, it says that this sequence of functions converges uniformly on E if and only if the Fn of Z is Cauchy for each Z and E. Now what does it mean to be Cauchy sequence? Cauchy sequence means that so for each epsilon greater than 0, there exists big M in the natural numbers such that when we have little m and little n greater than or equal to big M, that implies that the norm of Fn of Z minus Fm of Z is less than epsilon. So that's pretty nice because
So up above we had that it's uniformly converges if only n is, but this time we have an m. What does this m mean? Like what?
oh, well, the point is you want to look at two things in the sequence.
Oh, okay.
You know,
Okay, there's the m.
It's saying that the tail of the sequence gets arbitrarily close together.
Mm-hmm.
Sorry, I'm looking at the proof for a second here. There's something I'm reading about. All right, I'm going to move along here. So I say, next I say, Weierstrass taught us that uniform convergence of a series of functions on a subset of the complex numbers can be derived from the existence of a majorizing series. In particular, if a convergent numerical series bounds the values of a function on E, the series of functions converges uniformly on E. This is often known as the Weierstrass M-test. And so this theorem 5.16 affirms that the Weierstrass M-test holds for sequences of functions over an algebra. So this is the...
So this guy found it for only the complex, and you extended it into any algebra.
Uh-huh.
Okay.
And I mean, to be fair, I'm quite sure that Weierstrass's test has been abstracted in many contexts by many people in different places, but it's, you know. So Weierstrass M-test for A. So if you have a sequence, series, yes, a sequence of functions, sorry. We have a sequence of functions on E. So E is some subset of the algebra, right? And if we have this is convergent series, of real numbers. Okay, this is in R. Okay. And this is the majorizing condition. The sum of Fn of Z. Oh, excuse me, I keep putting a series. There ain't no sum there. I'm an idiot. And the norm of Fn of Z is less than or equal to m sub n. Alright. For all Z and E. Right, and also for all n, right? I mean, it has to hold for each n. Then this series, then Fn, so sum over Fn converges uniformly on E. Right, so this is a very useful theorem when you study complex analysis, like, and this is slightly to the edge of the undergraduate course. Like, we don't often, not every undergraduate complex analysis course is going to talk about like uniform convergence. That would probably be one of the more advanced courses out there, but this is very useful because it's not, there's like tons of convergent series of real numbers that you can refer to, and if you could just find one of those that's bigger than the norm of your functions with respect to the set you're interested in, you've proved uniform convergence. This is a pretty useful criteria when it works. So. And the proof, if you look at it on page 23 of the paper, basically the proof is just, well, if you have that the norm of the values of the functions are bounded by m sub k, where m sub k is the convergent, the kth term in the convergent series, then you can prove that the difference of the values of f sub I of z from m to n, basically the tail of the series of the functions is bounded by the tail of the series of the convergent real numbers. But since the series of convergent real numbers is since the real number series is convergent, you can make the tail of a convergent series as small as you like. So because of the bound we see in equation 70, it allows us to argue that in fact the sequence of partial sums of the functions satisfies the Cauchy condition, hence by theorem 5.15 it's also uniformly convergent. Now I think if you look at both of these arguments here, Audric, if I look at it, I think that these arguments are probably lifted nearly word for word from the standard arguments. There's no submultiplicative constant coming in here. It's like these are just, it has to do with triangle inequality and Cauchy arguments. I don't really see anything. I don't see any of the novel features in the proofs yet. Okay, so just saying, it's like if you'd already studied real and complex analysis, these would not be surprising. Theorem 5.17, it says if you have a power, so the real point of talking about this is, okay, I'm going to erase this stuff, all right. I'm trying to get through this faster. I don't think our research is going to end up being on the analysis side of things because like it's inappropriate to where you are at the moment. Yeah. But I just want to expose you this to what we've done. So I should try to go a little bit faster. Anyway, the point is the power series, right? What does the power series look like? It's something of the form, some Cn star z minus z naught to the n, right?
Yes. That's what I was thinking.
So this is a power series, right? And it is understood to be the limit of the sequence of partial sums, right? I mean, this is, what's the... I'll use J. 0, right? So this is Sn of z, right?
Yep.
And so that is a sequence of functions in the algebra. And theorem 5.17 says that it says that this, all right, so I need to, it defines a couple things. Alpha lim sup n going to infinity, the nth root of the norm of Cn, and R is 1 over m sub a alpha, where m sub a is the submultiplicative constant of the algebra. All right. What's the punchline? Punchline. The series is uniformly I say uniformly absolutely convergent. I'm not sure. What's uniformly absolutely? I think that may actually be a typo. I think we were saying uniform converges uniformly absolutely, and then at some point we realized we should just say converges uniformly and not say, I'm just going to say converges uniformly converges. Or uniformly convergent. On where? On z minus z naught less than or equal to r minus epsilon for any epsilon greater than 0. That's not quite true. And it can't be epsilon greater than 0 for any what? Epsilon where? Element of what? I mean, if we let r be, we can't let epsilon be larger than r because that would be troubling.
Less than r.
So it can be not quite 0 all the way to not quite r. Then also, if r is infinite, all right, then the series is uniformly absolutely convergent for z less than or equal to L for any L greater than 0. Let's see here, how can I say that? Now, how would r be infinity? What would that mean?
How would r be infinity?
Right, so like alpha equal to 0 gives r equal to infinity. That's what we mean by that. Like if this is 0, then we understand the radius to be infinity. It's a convention, really.
Okay.
But in that case, if this was 0, then this is uniformly convergent on any disk of radius L centered at z naught. Or center the disk wherever you want. It's actually, that's what the theorem says.
The MA alpha, when you plug alpha in for 0, it gives you something that just gives you.
Right, I mean technically this wouldn't be defined when alpha equal to 0, right? But
Yeah.
you understand in like this limiting sense, it makes sense to assume, like it makes sense to ascribe infinity to that case because you could write this differently. You could say if alpha equals to 0, then r
Why
equals to
would it
infinity.
be infinity though? Because like you could say it gets closer to like an undefined point, but not really infinity. Well, I guess that's both.
The smaller alpha is, the larger the radius. You know, but if alpha is small.
Oh, yeah.
But if alpha is.
There it is, yeah. I'm with you now. I'll stick with the other word of that.
So, again, this result mirrors the usual result, except the presence of the m sub a. All right? Now, Theorem 5.18 says that if you have a piecewise smooth curve of length L less than infinity, and you've got an open set which contains this piecewise smooth curve C, And if you have a sequence of functions which is continuous, a sequence of continuous a-valued functions on U, and if that sequence converges uniformly to f on U, then the limit of the integral, the term-wise integral of the sequence converges to the integral of the limit of the sequence.
Say the first problem.
So, like, the preamble to this is you've got the curve.
Yep.
Which I'm actually saying it's like, I think I just said piecewise linear just for the sake of, like this, you could prove this in a more robust category of curves if you wanted. I think I chose piecewise linear for the sake of like not lathering on too long about the, well, piecewise smooth curve though, that's not piecewise linear. Piecewise smooth just means that it's what we'd sometimes call an arc. So it could have like, this is smooth, it's got a kink, then that's smooth, and then this is smooth, it's got a kink. And so piecewise smooth just means you've got finitely many pieces, each of which are smooth, joined together at points where you'd have possible kinks or, departures in smoothness. You can define the integral over such a thing in a natural way. You just integrate over each piece separately and add them up.
Yep.
And so this is happening inside U. You have sequence of functions, and assuming it converges uniformly on U, all right, then, and we're also assuming that Fn, continuous. So it's a sequence of continuous functions that's uniformly convergent. Then here's the result. The limit, well, let me write this way. Suppose the limit as n goes to infinity of Fn of z equals f of z, right? So this is, let's call the limit of the sequence of functions f without the n, all right? Then the integral over the curve, all right, this is the curve, of f of z star dc, right, is equal to the limit as n goes to infinity of the integral of the nth term. But of course, you understand that we could rewrite this also as the integral. If you want to just get rid of the f and just talk about the sequence itself, right? This could also be written like this. Right, so this theorem, it's really about the interchange of the integration process and the limiting process.
Yeah.
It says the integral of the limit function is the limit of the integrals of the functions. So going back to your question, like, when can you switch limits? Well, uniform convergence is one possible way. And what this theorem says is, hey, if you've got a sequence of continuous functions in the algebra and they're uniformly convergent, then integral plays nice. The A integral plays nice with uniformly convergent sequence. Now, so if you look at the proof here, basically the proof is using the mammal theorem that I talked about for integral, that like the M sub A pulls out, and that's pretty much it. Yeah. Now this is also a well-known theorem for complex analysis.
Well, here it says, since using the symmetric of the a-Cauchy-Riemann equations we derive that, you can flip them. Oh, but then take the limit of that. Okay. Okay.
Yeah, I say, let's see here, what do I say then? I said in complex analysis, we learned one consequence of Cauchy's integral formula is that a uniformly convergent sequence of complex differentiable function has a limit function, which is likewise complex differentiable. However, in the absence of Cauchy's integral formula, we have no such luxury. In the study of differentiability of the limit function, we face the usual difficulty of real analysis, which is nicely addressed by Dudonné in 8.63 of, I think that's modern analysis. I forget what 7 is, just a second here. Click on that. What is that? 7. Foundations of modern analysis. So here's the thing: is differentiability is not as nice as integration. When you have, in terms of like sequences, if you have a sequence of functions where each one of them is differentiable, like, is it the case that the limiting function is differentiable? Not necessarily. In contrast, this theorem we just went over said that the integral of the limit function can be calculated. You know, well, did it say that? Well, anyway, that theorem said what it said. Let me not make it say more than it says. Anyway, so this is the theorem here, 5.19. Open connected subset of A, Fn A differentiable. All right, so you have an A differentiable sequence. If you have one point where the sequence converges, and then also for every point in the open set you're looking at, there exists a ball centered at that point, such that the derivative sequence, the termwise derivative sequence, converges uniformly. If you have those two conditions, then that sequence converges uniformly in there, and not just that, the limit of the sequence of functions, all right, and the limit of the sequence of derivative functions exist, and they're derivatives of one another. Like in other words, I say g of z is f prime of z, which is to say that's just to say that you can you can exchange differentiation with respect to z with the limit as n goes to infinity. Like this theorem 5.19, what it ultimately says is that the TdZ of the limit as n goes to infinity of fn of z is equal to the limit as n goes to infinity of dfn dz. This is not for free, and it needs the preconditions that are somewhat technical, but they're given right there in theorem 5.19. And so the proof basically follows the proof in Dudonné and paired with a place where I have to use the Cauchy-Riemann equations. All right, I'm not going to get into it. Like, but that's essentially it. Is that the proof in Dudonné adapts nicely here, and you can pair that with a symmetric Cauchy-Riemann equation argument to get the needed a differentiability of the limit function. I had to think kind of hard about this one, but I think it's mostly because my analysis education is not as deep as it could have been, perhaps. Anyway, so that gets us to corollary 5.20, which is one of the main events here, which is that if we have a power series in an algebra which converges for some disk of radius r, open disk of radius r, then we can differentiate term by term.
Okay.
And on a disk of smaller radius, all right, and the alpha is the lim sup of the coefficients.
So you can differentiate just like term by term, like how we usually do normal differentiation?
Yeah, so this is still that, right?
Yeah.
And it says...
So you just break it up. But when you break it up, like, is there a stop?
C ddz of the sum n equals 0 to infinity.
Yep.
You have like Cn star z minus z naught to the n. Right? It's equal to the sum. You could say n equals 1 to infinity if you like, right?
Yeah, so like, dz of, or could you also pull the Cn out at that point?
It's still a function of n,
Okay.
but you're just differentiating the term, right? I mean,
Yeah.
like ddz of z minus z naught to the n. This we saw last time, I think. There is the power rule.
Yep.
Like that, you know? So essentially we're just differentiating that with respect to z, right? But there's fine print. This is when? For z minus z naught less than what?
R.
Not r, but less than z minus z naught less than 1 over ma alpha. So the assumption was, so like we've assumed, you gotta be careful here. Me erase, this is no longer helpful. Because R is given differently in this theorem, in the sense that it's assumed, it's a presupposition of the theorem that you're assuming that you've got some n equals 0 to infinity of like Cn star z minus z naught to the n, which converges, what does it say? Suppose you get a power series which converges for z minus z naught less than r, right? So that's the precondition, corollary 5.20. You've got a power series in A which converges less than r, then you can differentiate term by term for that disk there. Now, of course, all right, so I guess, to be fair, the thing I just erased, what did it say? It said that this, dang it.
The soup alpha.
Did I erase that?
What is soup alpha? R equals a 1 over the m algebra of alpha.
Yeah, I think that was theorem 5.17, right?
Yeah.
Yeah, power series, you calculate the lim sup of the coefficients, define R to be 1 over m sub a alpha. Then we get uniform convergence.
Yep.
But notice that theorem 5.17 has z minus z naught less than or equal to r minus epsilon.
17?
Yes, theorem 5.17 does not give you convergence. Does it give you convergence less than?
On r minus epsilon.
I guess that does give. I'm sorry. This is where the. But epsilon can be made as small as you like. There.
Yeah.
So I do think actually that theorem 5.17 does give convergence. I believe that 5.17 can be. The question is, what's the difference between uniform convergence?
Yeah, we defined epsilon for it to be within the range of 0 to r and not touching you.
Yeah.
So
Okay, I mean, I guess theorem 5.17 and corollary 5.20, they're not so disconnected as I thought at first glance, but I was worried that, like, when you apply the derivative, the domain on which that calculation holds is getting smaller than the original disk of convergence, but I don't think that's the case. I think that the original R was basically, it could be made as large, it could be made arbitrarily close to 1 over m sub a alpha, right?
yeah.
And so this says that you can differentiate in the same place. It's good news. It's like there's nothing weird happening with the domain shrinking as you take derivatives. Of course, what's more interesting is in the case that alpha is 0, right? Because if alpha is equal to 0,
It's infinity.
right? And so then you can just term by term differentiate to your heart's content on the whole of A. Corollary 5.21 says that if you have a power series which converges, then it has derivatives of all order. So it's what you might call A-smooth. And you can take those derivatives on the disk of, well, ball really, of radius 1 over m sub A alpha, where again alpha is the lim sub of the nth root of the norm. And the higher derivatives are defined in the natural term by term derivative way. Okay. Now, definition, a function from A to A is called entire if it can be expressed as a power series which converges on all of A. So entire functions are special in that they permit the representation by a power series which is convergent on the whole of A. Okay? Any question?
No, it's just like, are there certain power series where it doesn't converge?
Oh yeah.
I mean, well, that's a dumb question, but I mean, like, wouldn't all power series that converge naturally on the algebra, like, wouldn't that they all, like, I feel like this one's kind of like a
So
Because if you have a power series that converge on, like if we had, like, you know, if power series converged on the reals, like, there's no point on which it doesn't converge, right?
but the what's being defined there is the word entire for a function.
Mm-hmm.
So like I guess my go-to example would be this function. You know, what's the domain of that function?
Infinity.
Right, yeah, I
You
mean,
can go either direction.
exactly, no problem, right? You can differentiate. You see that you do no division by 0.
Yep.
And basically the graph looks like 10, right?
Yeah.
Largest it ever is at 1, and it kind of just does one of these deals, right? So it seems harmless enough. So, okay, is this function, I mean, it's got a domain, the whole reals, but is this an entire function?
Not at the point that it crosses y, right? Because if you turn it, like, well, it can be written as a power series, because you could write it as
Now, yeah, power series, if the power series exists for a function at a point, it does so uniquely because the derivatives of the function at the point fix the power series, right? They generate the Taylor series,
Yep.
which, if the function is analytic at that point, represent the function near the point. So, like, what's the power series of f centered at 0? Right? Because if this function was entire, that power series at 0 would have to go on and on.
yeah.
Does it? See, we can use geometric series in this case to kind of like shortcut all that differentiation.
Yeah.
This is just a trick. But this is 1 minus x squared, right?
Yes.
So that's the sum minus x squared to the n, right? N equals 0 to infinity. In other words, that's the sum n equals 0 to infinity of minus 1 to the n, x to the 2n, right? This is the power series representation of 1 over 1 plus x squared at 0. The Maclaurin series, yeah. So is this function entire? Well, what's the...
It's missing all the odd coefficients though.
That's not why. The question is, what's the radius of convergence? See, if this was an entire function, the radius of convergence for this has to be infinity. It has to converge on all of the reals. But the radius of convergence for this is given by the theorem for the geometric series. Geometric series says this step is only legit for the radius less than 1, right?
Yeah.
But here the radius is x squared, minus x squared, right?
Mm-hmm.
Which is to say that this is for minus 1 less than x less than 1. So this has IOC minus 1 to 1,
Mm-hmm.
which of course is not equal to the reals, right?
Yeah.
So this function is not entire.
So for it to be entire, it would have to have IOC of the reals. Okay. And that would mean so that would just mean the domain of the geometric series would be infinity to infinity.
There are plenty of functions like that, functions that you know.
Yeah.
This is not one of them.
Mm-hmm.
Now the reason that that happens becomes apparent if you look at this as a complex function. Like if you think of this as a complex function, the corresponding complex function f of z is 1 over 1 plus z squared, right?
Mm-hmm.
Well, that's 1 over z minus I times z plus I, right?
Yep.
So when you take a complex perspective, you've got singularities at I and at minus I, right? So when you try to make a power series centered at 0,
You wouldn't get points then.
power series centered at 0, you run into those singularities. You run into those singularities
Oh.
when you get to a disk of radius 1, right? So it just so happens that that 1 and minus 1, that's the real. Of course, if you restrict this to the real line, you get that, right?
Yeah.
So sometimes you can understand the limitations of a given real series by taking a complex viewpoint. See, because there's no problem with this function in terms of just real calculus.
Yeah.
I mean, heck, you can even integrate that thing to plus and minus infinity. It gives you pi.
Yeah.
Because you have your arctangent integral. This is an important example. But anyway, we all have more to learn about analysis, right? So this is just a sort of cautionary tale. Not every function is entire. But what Theorem 5.23 says is that if you do have a function which is entire on the reals, all right, and you have a series, a real series, right, then there exists a unique entire extension to the algebra using the same coefficients. So the theorem, if f of x equals the sum n equals 0 to infinity of a n x to the power n is entire,